So you take a state vector A, B vertically, you convert into a row vector A, B, that will be a bra. So that is the Dirac notation, and this is the reasons as to why we are using the basically compactness and scalability. Scalability, we will see why scalable. As we have more number of qubits, you can ingest everything into a single. So it's like suppose your vector is, suppose this is a state vector, right? In quantum mechanics, we are calling it as wave function. Now I'm going to start talking as state vector, because that is giving the state of the system at a given point in time. So this one can take different values, 0 or 1. So if it is 0, then it has its own column vector. If it is 1, it has its own column vector. And if it is single qubit, you are only supplementing it with single digit with either 0 or 1. If it is n qubits, or let's say 5 qubits, then 0, 0, 0, 0, 1 can be within this bracket. So it acts as a compactness to consume more qubits within a single space. That is the advantage of Dirac notation. So this I just discussed. In classical terms, we have 0 and 1s, different ways in which we can realize 0 or 1. Either you can give 5 volts for 1 and 0 volts for 0, or you can use magnetic domain, magnetic material on tapes and all to distinguish between zeros and 1. In quantum, instead of zeros and 1, we are saying it is the simplest quantum system. So going forward, qubit is nothing but a simplest quantum system. It's a quantum system by itself. So it can do, I mean, we can extract information out of it, and we can perform operations on it. Operations means we are trying to apply gates. It is quantum operators in quantum mechanics. It is gates in quantum computing. So now we will take a basis vector, basis 0 and basis 1. Instead of real and imaginary in quantum, in complex numbers, we are going with basis vectors, basis 0 and basis 1. And we have the state vector, instead of wave function, I'm calling state vector now, can be represented as the combination, linear combination, in linear algebra, right? Linear combination of the basis vectors. You can take any basis vectors. I'm taking ket 0 and ket 1. So that's how you pronounce ket 0, ket 1. So basis vectors you are taking, you are doing a combination, linear combination, and you are getting psi. Now here alpha and beta are the amplitudes of the corresponding ket basis. Now what will that give us? It will give possibilities, probability basically, right? So it will tell us, now if you want to know what is the, if you want to measure and get the outcome, you basically have to solve this, right? This is the wave function we talked about. You need to apply something to get, to make it. So what do we do? So here, all this space in which the state vectors exist is called Hilbert space. Hilbert space is like complex space, just that it can accommodate additional features like inner products of two vectors can exist in the same space. It will also have a limited functionality. When you apply a limit on it, it is bounded. So this Hilbert space is nothing but a complex space which will have these additional features, and we are taking. So this is basically, I'm trying to set some of these as the basis to move forward. In this context, I'm also saying linear combination I'm using. Linear combination is nothing but superposition. Mathematically, it is linear combination. Physically, it is superposition. And everybody, I think Manish Bali also gave definition of superposition in the morning, right? So superposition can have different definitions from physics world, but mathematically, it is linear combination of basis states, what you define a quantum state with. So that's the mathematical way to take superposition. It's an intuitive way to understand superposition, so that we don't have to worry about, because superposition and entanglement sounds like science fiction. So we'll go with math, which is a standard. And the constraint that everything works is based on this normalization effect, because the probability density function, sum of all probability should be 1. So we are taking the amplitudes of this linear combination, and we are saying the squared mod of square of each of these coefficients is 1. That's a normalized constraint that we have to set. So this is a setting for quantum computing, that we need these rules to apply the normalization effect. We should have a basis vectors, and we are in Hilbert space. These are the formulation of quantum state. So to define quantum state, it's a state of a qubit. It's a normalized unit vector in 2D complex space. That is a definition of the state of a qubit. If somebody is asking what is the state of a particular qubit, it's a unit vector basically in a complex 2D space. This is a complex 2D space. And here alpha and beta are not real numbers. They are complex numbers. Because we are talking in the complex world. So everything is complex. So here, as you can see, I have represented alpha and beta vertically because it is a column vector, ket representation. Ket psi equal to alpha ket 0 plus beta ket 1, and alpha beta are coefficients. We represent vertically, alpha beta, column vector. Now, we are giving definitions of the basis vectors also. We defined basis vectors I took as ket 0 and ket 1. So how can they be represented in a matrix format? They are column vector 1 0. 0 is 1 0, 1 is 0 1. These are important definitions that we will have to know in order to perform gates, in order to apply gates in the future sessions. So now that we know the definition of ket 0 is this and ket 1 is this, when you apply those into this for psi, alpha 1 0 plus beta 0 1, we are getting that. How I got is like this. So basically we are applying 0 and 1 here, and we are getting alpha beta. So in the end, it turns out that alpha beta are vertically stacked amplitudes, right? So the amount of alpha is directly proportional to outcome that 0 can get. I mean, the result psi, if when you measure, the outcome can be either 0 or 1 ket, right? So how do you know 0? It depends on the amount alpha has. So this will basically, if alpha is more, we get 0 as output. If beta is more, we get 1 as output. So the amplitudes actually determine the outcomes. Of course, noise is there, everything is there, that all we have to control, that is always there. So assuming all that is controlled, this is how it is. So slowly we are shifting gears to quantum gates. The first gate that we will discuss, so that's the only gate I'm going to discuss, because all the future FDP sessions have so many sessions on gates, so I don't want to overlap. But I want to give a notion on what gate is doing. I'm going to take NOT gate. A quantum gate manipulates the state of qubit. So I'm taking some qubit, it is ket psi is a qubit, and I apply a thumb gate. Any gate I apply, it is the reason I'm applying is I want to manipulate the state of that particular ket psi or wave function, right? State vector basically. So if you want to do any operations, because we want quantum computer to perform operations. To perform any operation, we take the state vector, apply gates as you want, and then you get the result. So a NOT gate, like in classical world, if you give 1, it outputs 0. If you give 0, it will output 1. So it just flips the input. So we want the same functionality in quantum world also. So if we are sending and we represent NOT gate with this symbol X, and if we are applying X on ket 0, we are expecting 1 as output, and if we are applying X on 1, we are expecting 0 as output. So this is our expectation of how the NOT gate should work, and this is analogous to the operators that we discussed: position operator, momentum operator, energy operator. That you apply operator is on the left, apply on the, there it is wave function, here it is state vector. That is a transition. We are just setting how we can derive X gate, right? So consider this. We always talked about that vector, right? Psi, ket psi. Ket psi is nothing but alpha ket 0 plus beta ket 1. So we are trying to apply X NOT gate on that particular state vector. And remember, even in classical world, linearity applies for all the gates. Similarly, here also linearity applies. So X applies on first qubit, and then it applies on second qubit separately, and we expect output alpha ket 1 plus beta. So basically it flips. That is the expectation, and it does that way. How it does, we'll see in the next slide, but this is the expectation. If it is applied on 0, we should get 1. Same thing, linearity is applicable. Earlier I did not discuss any properties because I assume everybody of you are aware of all these properties, all the linearity principles, distributive properties, commutative properties, all of those scalar properties, all of them apply to all these operations. Now this is how we represent quantum NOT gate. So you have a state vector, you apply quantum gate on it. So the input is state vector, you apply quantum gate, what is the output, right? So if you are in the place of state vector, if you are sending 0, get 0, we should get 1. So this is called as quantum circuit. The smallest quantum circuit is quantum wire. That means there is nothing, no gate, just wire. And in classical world, it seems obvious. Wire is wire, you give input without any resistor or capacitor or anything, you should get the same output. That is obvious, and everybody will expect the same. But in quantum world, you give input in a quantum wire, and you are expecting the same thing. We all expect the same thing, and it will give same thing, provided there is no noise. So getting the same thing without having gates itself is a difficult task in quantum hardware. That is the toughest part. So assuming that is all solved in quantum hardware, all the noise problem and everything, then we are placing gates in the quantum wire, and we are calling this as circuit. This is the next smallest circuit. And morning Dr. Manish Bali has shown even a bigger quantum circuit. In the next slides, sometime I will also show one more circuit which has a number of gates and how it will. So when you apply a gate, you will expect outcome. And for every gate, there is a matrix form. And the NOT gate in quantum computing has this form. It takes this form, and every gate is a square matrix and follows certain rules. They are unitary matrices. Anybody can tell what a unitary matrix is? Just a question. No. Sorry? A transpose is equal to 1. A transpose? A transpose, a complex of that must be equal to the... complex, that is important. Complex. So if you take any matrix A, you take a transpose and then conjugate and multiply with the same matrix, you get identity. Those matrices are called unitary matrices. So transpose, conjugate. Transpose, I think most of you know. Conjugate is, if you have A plus IB, conjugate of A plus IB is A minus IB. You just flip it. That is, so every gate in quantum should follow unitary principle, and everything will be a square matrix. So the important thing here I want to show is, if you are applying 0, I told, if you are applying NOT gate on 0, we should get 1. How we are getting 1 is, you put the matrix, and you know 0, we already have the definition. It's a column vector 1, 0. And you do the multiplication, you get 0, 1, which is nothing but, this is the definition of ket 1. So likewise, mathematically, every gate, if you multiply with the respective input, here the input is very simple input, which is 0 ket. But inputs can be complex, right? It can be having multiple different vectors. So in such cases also, you just have to multiply the gate matrix with the input matrix, and you will get the corresponding output matrix, and you know what is expectation, right? Means what you are expecting out of it. So all that we should know is the gate matrix. That is important. So NOT gate has its own matrix. So here I want to show that every gate has a matrix form. Every gate has a physical form like this, notation wise, and every gate is square matrix. And yeah, those are the 4 things I want to tell. Yeah, this we already discussed. Okay, flips. Any questions so far?
So this matrix form will vary from gate to gate?
Matrix form will vary.
Matrix form what we have written here for size equals to 0, 1, and 0 for the NOT gate.
Yeah.
Yeah. That form, will it vary from gate to gate or it will be?
This is X gate. Sorry, NOT gate. This is NOT gate. If in quantum computing anybody is saying NOT gate, that is a matrix form. It is constant. This is NOT gate. This is constant. So there are, I'm only telling about NOT gate. There is Hadamard gate. There is Pauli X gate, Pauli Y gate, Z gate, C NOT gate. There are many gates in quantum computing. Every gate has its own matrix form. I'm only giving today one example, one gate today, right? And that gate is simple gate, and this form is fixed. NOT gate is always like this. Yes. And whichever gate you go through, it will have its own representation in the circuit. Circuit I'm calling because if I think morning only you asked about IBM, right? So if you log into IBM website, in the quantum computing website, you can formulate gates. So there will be drop down gates. So you can pick and drop, yeah, circuit to form. Okay, so in the IBM portal, when you go into quantum computing website, so you will see that you can drop down any of these different gates from there. So the moment you see X, you should know that it is NOT gate. So if you see H, it is Hadamard gate. So any gate you are studying yourself, or if you come across, you will please remember that it will have its own notation. It will have its own matrix form. And if you want to know what is the input and what will be the output, you first multiply with 0 vector, ket 0, and whatever outcome comes, you'll know how it is. So it is basically it is linear transformation, linear algebra actually. Transforming the input to an output, the transformer, the thing which is transforming is the gate, right? So that's what it does. So I just want to give you a sense of how gate looks like and its matrix form, that's all. And I'm not going deep into superposition and entanglement. I know it is the hot topic, but I want to tell you that this is a special state, and this is a superposition of all this. The system is in many states at once. It's not the thing. System is not at many states at once. Of course, physically, when you say like that, yes, it is in many states. Until the measurement, we don't know, but this is a representation of superposition. How do we achieve this? You have to use Hadamard gate to achieve superposition. So Hadamard gate I'm not covering here. It has its own matrix form. If you multiply that gate with a ket 0, you will get this as output. So to perform any quantum operations or quantum manipulations, you have to get the input into superposition first. And for certain application, you want to get into entanglement also. Entanglement beauty, I'll show with one example. I'll show why entanglement matters and what is the beauty of it. But somebody says that you want to get the input into superposition, you apply Hadamard gate. So that is our tool to make the input into superposition. So to make ket 0 into superposition, I apply Hadamard gate. It will come into this state. So yeah, this is always the thing, right? Before measurement, state will evolve smoothly, rotations are deterministic, no randomness. Basically, until you take the measurement, state will be nice. It will be unaffected, right? The moment you take the measurement, the state collapses. You can no more repeat the same experiment. You can't re-get the same answer again, because it collapsed. Yes.
So maybe I'm asking a basic question.
Yeah, sure.
So in the not gate, you are showing the unity matrix.
Yeah.
0, 1, 1, 0. So that's why. So you are telling that imagination. So in the actual one also this thing, if you give 0, it will become 1. But here in your actual gate, it is always you have to think that it is like that.
It is like that. Yeah, meaning you are saying that how come this form exists? Huh?
Yeah.
This is found. They tried emulating our classical NOT gate. In classical world, you send 0, you have to get 1. So what is that in linear algebra that can get you from ket 0? We have defined initially in the previous that ket 0 is nothing but 1, 0. What will give you when you send 1, 0 column vector when you multiply as 0, 1? This is the matrix, and that matrix is not, and it works not only on basis vectors. So 0 and 1 are basis vectors, right? Ket 0 and ket 1. It works on every vector. That is the beauty. Yes, it flips. That's the beauty of that matrix. It flips. It works for every vector, not only 0 and 1. We also tried on psi, right? You saw here psi. What is psi? It is alpha 0 plus beta 1. And it clearly was able to flip because linearity, right? So no matter whatever input a vector you give, it will flip. So that is the beauty of that particular matrix. Similarly, Hadamard gate, the beauty of Hadamard gate is no matter whatever input you give, it will put in superposition. That superposition what I talked about. We want that. Why? Because it will serve certain purposes. And there is if you pass a given input to Hadamard gate and pass it to another gate called C0 gates. So till now I am discussing about single qubit gates. Your input is single qubit, right? For NOT gate is a single qubit gate. Hadamard gate is a single qubit gate. But there are 2 qubit gates like C0 gate, where the two inputs are given to a single gate. So if it turns out that, I'll show an example later, where you pass first input to Hadamard gate and then pass to a C0 gate, you get entanglement as output. So somebody wants entangled state for any given state, you first pass it to Hadamard gate and sequentially pass it to C0 gate, you get entangled state. I mean, this is experience. Because you keep multiplying matrices, you'll come to know. Oh, if I multiply with Hadamard and then C0, you get this. Experience means after multiplication, people found out. And for every vector, input vector, it happens like that. So that formulation of that matrix form itself is beauty. Yeah. So entanglement is this state. This is also called as Bell state. Everybody calls it as Bell state because they take that. So in physics people talk about this. I think most of you know. If you don't know, you take 2 electrons, or let's say Alice and Bob are there. You give 1 electron to, or 1 coin to Alice, another coin to Bob, and ask them to, and let's say these 2 coins are entangled. Suppose you entangled is a phenomena you did, suppose it's a magic, you did, and then gave it to Alice and Bob. You ask Alice to go to Venus, you ask Bob to go to Jupiter, right? After 10 years, ask them to flip the coin, right? If Alice would have got heads, Bob will get tails. And they will communicate over radio wave so that they want to know what is the outcome of each of their experiment, flipping coin. Actually, before the communication, because communication will take a lot of time, right? Radio waves from Venus to Jupiter. But before that only, Alice can know what is the outcome of Bob. Bob can know what is the outcome of Alice. Because Alice got head, she knows Bob would have got tail. Because they are in an entangled state. So entanglement is, irrespective of the distance, if two objects are in entangled state, if the first object is turned out to be North Pole, second will be in South Pole, no matter what. How it happens, nobody knows. Right?
Against the theory of relativity.
Yes. So that I can't explain. So, so the thing is, in quantum computing, mathematics, if you go, physics, if you leave, this is the entanglement state, and it's called Bell state. So the thing is, many systems in one state. One state means, yes, sir.
In the entangle,
Yes.
you explained about one particular
Yeah.
concept, right?
Yeah.
But if it is multiple outcomes are there, suppose something like
2 qubits.
your tile and head is okay.
Ah.
That is
Ah.
clear.
Yes.
But if you have more than one,
So in an entangled state,
more possible combinations are
it is generally paired, sir. It is paired. Yeah. Even if more are entangled, many systems one state, they will all cohesively work together. How they are working, we don't know they're working. So theory-wise, it is many systems one state. So here in the 2-coin example, 2 coins are 2 systems, 2 different systems, because 2 separate experiments you are performing. But they're in one state means if one is positive, other one is negative, or one is head, other one is tail. So that if this is head, this is tail. So the outcome, right? Outcome state is same, but 2 separate systems are taken for experimentation. So many systems are possible according to theory, but no such example. Yeah. So I'm not digging deep into entanglement and superposition, but my interest is actually to show the transition from quantum mechanics to quantum computing. And then we applied gate. We are trying to look at, we'll discuss briefly about measurement. We discussed about measurement earlier, that wave function collapses and it shrinks and we can not reconstruct again, right? Here measurement, we are talking about measuring a qubit. So if you take state vector psi, which is represented by this, which we have been discussing for some time, can I just measure it and read out alpha and beta like parameters in a signal? Can we really measure alpha? What is the value of alpha and what is the alpha of beta? Sorry, value of beta. We cannot do that in quantum computing. And unlike a traditional world, right? We cannot do that. And then it is important that you get a classical output. Outcome 0 occurs with probability alpha square, alpha mod square. Outcome 1 occurs with the probability. So we can only get probability distribution. And using the probabilities, we can determine what could be the output. So if the outcome is 0, the qubit becomes 0 ket. One thing I forgot to tell you earlier is that 0 ket is not 0 vector. 0 ket is 0 ket. It is a column vector 1, 0. 0 vector is actually, I'll switch a little bit. So this is ket 0, this is not 0 vector. 0 vector is here, this point. 0 vector is this point, origin is a 0 vector. This is psi vector. This is ket 0, basis vector. This is basis. So that's a difference. So we will transition slowly to this. But before that, I will switch to the paper that discussion of article is one of the theme between. So I've written my own paper, swinging between classical and quantum bits. The idea of this paper is to tell, this is again published externally by Dell Technologies. The idea of this paper is to tell that we have information in the classical world. We always need it, right? We can't just have a quantum computer and do everything with it. Why we we have to send this into quantum, get some processing done, and then again you have to convert back to classical. Without converting it to classical, it remains in the complex world, complex space. So you need a real-time measurement, and the output should be in real space. So that is the swinging between classical and quantum, is why I gave that. I'll just show this, the AICTE that we discussed so far. I'll just browse through. If you pass state vector psi, which is alpha ket 0 plus beta ket 1 into this, it flips. And if you once again apply NOT gate, you will get flipped again, which is nothing but a quantum wire. Basically, giving the input, apply 2 gates, you get the same output. Right? Because you flipped once, you flipped again, you get the same thing again. So it is nothing but 2 NOT gates in serial is nothing but a quantum wire. And next comes the Hadamard gate, which I did not discuss, but this is the matrix of Hadamard gate. H equal to 1 by root 2 of, this is the Hadamard gate. And you apply 0, I mean Hadamard gate on ket 0, you get this output. I can expand. So basically, again, matrix multiplication. And as I told earlier, this is nothing but superposition. If you apply any input to a Hadamard gate, you get superposition state. Same thing for ket 1. This is also superposition state. Though it has minus, this is also superposition state. So whether you apply 0 ket or 1 ket, so Hadamard gate onto either of them, you get superposition. Same thing here. We are applying Hadamard gate on state vector psi, you are getting superposition here. With different coefficients, of course. Coefficient doesn't matter, but you are getting superposition. This is a 2-bit gate, 2-qubit gate. Instead of a single qubit gate, this is a 2-qubit gate, and you apply inputs, you get the corresponding output. This is called C0 gate. It has its own matrix. I'm not covering this, but allow other. This is a matrix associated with C0 gate, and I told you earlier that a Hadamard gate and C0 gate in sequence would give you entangled state. So I want to cover a little bit of this setting to just to give you idea how we can leverage quantum computing for real use cases. If the use case, here the use case is, this is called superdense coding. Here the use case is that if there is a requirement, so generally, if you want to transport a classical bit via qubit, you need 1-to-1, which means if you want to transmit 4 classical bits, you need 4 quantum bits. But here, if the state is in entanglement state, you can transmit 4 classical bits using 2 qubits. That's what I want to show, that how entanglement will enhance communication. This is used in quantum communication or quantum cryptography, you can call. So here in this case, Eve, we have 3 people, Eve, Alice and Bob, and Eve has 2 qubits. Eve will send 2 qubits one over to Alice, other one to Bob. So the bottom one is going to Bob, the top one is going to Eve. Before Eve sends those qubits to Alice and Bob respectively, Eve is going to apply Hadamard gate and C0 gate. Basically, Eve is trying to put the state as entanglement state. Eve is trying to put in entanglement. Once both of these qubits are in entangled state, whatever Alice has done, Bob will know. That is the idea. That because one of the qubit is transmitted to Bob, that information is enough for Bob to kind of retrieve what the other qubit is. So that is how entanglement helps. So you don't have to send all the bits, all the qubits to the sender. With one qubit, Bob can retrieve what Alice you would have sent to Alice. So for that, so we'll begin with the first half, the first part, which is Eve sending to Alice and Bob. So we have 0, 0. When 0, 0 is sent to Hadamard gate, the outcome is this. Now you represent. Earlier we were only talking about single qubit in the ket. So when you have 2 qubits, you represent it this way. You have 3 qubits, it will be 0, 0, 1 or 0, 0, 0. So that's why this bracket notation is very helpful in doing these computations. It is compact and you can do all the manipulations easier. That's what we discussed in Dirac slide. So the outcome of this here is it is 0, 0 plus 1, 0 by root 2. Why? Because the Hadamard gate, I did not explain the matrix, but if you multiply that Hadamard gate matrix with 0, 0, you will get this as output. And the C0 matrix, again, if you apply, you will get this entanglement state. So any input, if you pass, you will get an entanglement state if they are in sequential. Here, Hadamard gate and C0 gate. This is a quantum circuit. Basically, we are discussing quantum circuits now. So when you are preparing any algorithms, you have to formulate the circuits in the order in which the operations or manipulations has to be done. So you might have certain need. Suppose Dr. Bali sir said Shor algorithm, right? It's an algorithm which will factor. So Shor algorithm is nothing but if you give a huge number, it will find out the factors of the given number. That is a Shor algorithm. If you want to code that, you can code and you can prepare. For everything, you have a code and a corresponding circuit. So coding will help you build the logic and circuit will help you physically realizing what operation is happening. So without that, you will not be able to code, right? Because you need to know mathematically, if you want certain output, you can multiply and come to know what outcome you can get. So this is the 2 ways in which you can do. Either you take the algorithm, do it, or you put the gates together, finalize the circuit, and then convert it into, I think, P-Spice or something is there, right? In electronics, they used to like put the, I did long time back, but something like that. So you can format the circuit first, get the code or do the code, and then create the circuit. So once Eve sends this entangled state, so Alice wants to, these are the classical bits, 0, 0, 0, 1, 1, 0, and 1, 1. So Alice got this qubit, entangled state. Now Alice, if she wants to send 0, 0, she will not apply anything. Basically, I is identity matrix. So if she wants to communicate Bob 0, 0, she will not change the input. She will send as it is. What is the input? This is the input, entangled state. No change. It will come as it is. This is what she is sending to Bob. So if Bob receives this, Bob clearly knows that Alice wants to send 0, 0. So using single wire, Alice is able to send 2 classical bits. If Alice wants to send 0, 1, she will use X gate, which is our NOT gate. Apply NOT gate on this entanglement, it will flip into this. I mean, if you multiply with matrix, you will get this output. And if Bob receives this, he knows that Alex is sending 0, 1. So basically the analogy is how the input is getting transformed. Based on that, Bob knows what classical digits Alice wants to send using a single wire, using a single qubit. So using a single qubit, we are able to transmit 2 classical bits. That is what is called superdense coding here, because we are able to use entanglement feature to send multiple classical bits within a single qubit. That is a crux of this entire story. Any questions on this?
And repeat the sentence.
Okay.
Repeat the last sentence.
Last sentence is, are we able to send? So generally it is like we can only send one classical bit over a cube using one qubit. If we want to send 4 classical bits, we need 4 qubits ideally. What I'm trying to tell you here is, using entanglement state, which is a special state, it is possible to send 2 classical bits using a single qubit. That is this experiment is telling. So this is able to improve the speed because we are able to perform multiple operations. We are able to, with less number of qubits, we are able to perform more number of classical operations. That is the indirect outcome of this whole thing. So that's about this. Okay. So Dr. Manish Bali showed you already this quantum computer. The quantum chip is at the bottom, and the whole apparatus is to bring down the temperature, and this will be usually near absolute zero, approximately 15 to 20 millikelvin is the temperature over here, and stage by stage the temperature increases. This will be at room temperature, and this will be cooler than that, this will be much more cooler than that. As we go bottom, it will be much more cooler, and they use some system called, as I'll show you, cryogenic systems to get that cooling done. So quantum hardware, just moving to quantum hardware, I'm not a specialist on quantum hardware. Most of my work is into those algorithms, but just want to cover everything. It's a physical machinery, right? And these are the 3 things the hardware should be able to do, basically. The 3 things is, it should be able to hold information. That means it should give you qubits, because without qubits, why do we need that hardware? In the end, qubits matter to us. And building a system with more qubits is a challenge today. As you have seen in the morning, the quantum computer in the world that we have more qubits today is 1121, right? That is the highest number of qubits that we have. But to break RSA algorithm, we need 1 million qubit. So where is 1121 and where is 1 million, right? So there is a gap absolutely with respect to the hardware development, not with respect to algorithms. We have ready-made algorithms. We have all the gates necessary. We have everything ready, but we don't have system ready. So we are in state that we are waiting for the hardware to catch up. So 1121 is from IBM, and Google is with 105 qubits, Google Willow chip. And then rest follows. Everybody is trying. But essentially, the first one is very important. It should give you qubits functionality, physical qubits I'm talking about, because we are going into hardware now. And it should allow us to apply quantum gates. That is another important thing. Third thing is, it should have apparatus to let us measure when needed, and without noise or without all those constraints that we talked about. So these are the 3 important things, and a quantum computer will have all these 3. In addition to that, it will have this controlling, and it will have a stabilizing environment, because all that it has to provide along with. So it's a huge system. And then we are talking about approaches, quantum hardware approaches. We spoke earlier about vacuum tubes and semiconductors for classical world, right, for electronics. Similarly, there are many approaches. Superconducting qubits is one approach. Companies like Google, IBM, and Rigetti are popularly using superconducting qubit technology to make their quantum hardware. All 3 are top in the race, which means probably superconducting qubits is the right choice, probably, I don't know, but looks like. And they use this superconducting materials like aluminum. Basically, they use these dilution refrigerators. They are nothing but those cryogenic systems which will cool these metals to, here it is like 15 millikelvin. temperatures. That's the important thing. And the physical qubit, now that is the hardware we discussed so far, right? Take the metal, bring it to that particular temperature, your metal is ready. Now, after your metal is ready, what we need? Physical qubits. The physical qubit is realized by that electrical current. So basically, there is some junction called Josephson junction that forms in that particular superconducting material. And at that junction, the electrical current that passes, if it is, so how to determine? We always want 0 and 1, right? That's the ultimate thing that we are looking. So we want something to tell something is 0 and something is 1 bit, right? So that is told by this specific energy level of oscillation. So higher energy level, so basically 0, otherwise it's 1. It is 1 actually, not 7, my mistake. Higher energy level is 1, lower energy oscillation level is 0 for this electrical current. So that's how this hardware is leveraged. The next one is trapped ion qubits. This is another technology, another approach to quantum hardware. And this is popularly used by IonQ and Quantinum. Our company Dell is partnering with IonQ to promote their quantum hardware. And along with that, our company actually provides a lot of high performance computing hardware, so that the performance doesn't degrade once you get the output from a quantum computer. You need a HPC systems to carry forward the rest of the classical operations. So IonQ is one of such company, and here the best, it is comparably slower to the superconducting, but the accuracy is very high, which means basically the noise is comparatively low, which is why the accuracy is more. Here the thing is, it uses this the electron, right? So basically ions is nothing but electrons. If electrons are closer to nucleus, it is 0. Excited state, which means in the outer shell, then it is 1. So they kind of take the state at which the electron is and accordingly tell whether it is 0 or 1. Third one is photonic qubits, uses light. Photonic itself tells you that it is using light. And Xanadu and PsiQuantum are the companies positioning their quantum hardware based on this photonic idea. And the physical qubit is nothing but single particle of light, which is nothing but photon. And 0 and 1, there are 3 different ways in which one can tell whether the particular photon is 0 or 1. So I don't know, Xanadu uses, generally one of them is what one company will use and the other one other company will use. Polarization, so if oscillation, horizontal oscillation, if it's that particular property of photon, if it is horizontal, having a horizontal oscillation, it is 0, vertical means 1, and so on and so forth. Basically, they're basically taking properties of the photon as considering as whether it's 0 or 1. This is spin qubits. This is, though Intel is actually also investing a lot in quantum, it doesn't have a product yet outside, but they're using this spin qubits. There's one more company called SpinQ, which is doing a lot of interesting work in this area. They're also, their company name itself is SpinQ. So here they take a standard silicon chip like electronics, and here they look at the spin of the electron, whether it's north pole or south pole. Accordingly, they determine whether it is 1 or 0. So these are the 4 popular, I mean, there are around 8 to 9 different approaches so far, but I picked only 4 because these are the 4 approaches which popular companies have been using to prepare quantum computing. So this is a cryogenic system that I was talking about, which will try to bring the temperature to sub-milli-Kelvin level temperatures. And these are very expensive and bulky. Because they are bulky and very expensive, it is quantum computers are not something which we can buy and keep it at home. It requires special environment. It requires a lot of investment. And generally speaking, quantum computers will be probably cloud-based. I don't think even enterprises will purchase those, because it is not only the cost that it is required. You need people who can manage those in your data center, which is very challenging to get, and this technology keeps changing, so it is better to use from cloud. So IBM has set forth, IBM and AWS, AWS has, I think, Bracket as a service. AWS Bracket is a service. You can go and buy. I still recommend IBM, but anyway, that's a different thing. So IBM, why? Because IBM is like pioneer in both software stack as well as hardware. They have Qiskit. I'll just glance it through that software frameworks as well, which it's like Python. So you can, somebody who is very much acquainted with Python can easily change gears and use Qiskit. Of course, Penny Lane is also Pythonic little bit. So these are all the notable companies, and the qubits, I probably did not put IBM number over there. The 1121 is the number of qubits that they came up with. Of course, the roadmap has much more ambition. So these are the different companies, and so moving on to quantum applications, the most obvious application is quantum chemistry, because of the reasons as to why drug discovery is very difficult using classical computers. So always they tend to kind of try to experiment a lot of chemistry related algorithms, right? So here is the problem, and the way I have put applications here is to tell what the problem is and what quantum is providing as a solution. So the problem is that a molecule, if they want to simulate on a classical computer, as the size of the molecule is growing, the amount of computations required is exponential in nature. I will briefly touch on the complexity theory towards the end to give a glance about what maybe you are familiar with complexity theory, but I'll just draw some comparison here. Here it is exponential in nature. So complexity is exponential, EXP. So it's not possible for some of those. That's why quantum is obvious, because quantum computer doesn't model the electrons, because it will really act like it, because it is electrons is what we are really taking, right? So that's a fundamentally useful way. The next one is optimization. Most of you would have known this traveling salesman problem, which is very popular. We all know how difficult it is, and let's say if you need to find 100 locations delivery or something, it's very difficult to find shortest path and or optimum path. So quantum annealing is another concept, this kind of algorithm that you can use to kind of solve this traveling salesman problem. The analogy is that suppose if it is stuck at a valley, the optimization, right? Quantum computer can tunnel through the hill, find a deeper valley, is the idea. So optimization can be used in finance. Quantum finance is a very promising domain, and for a lot of people who are doing stock market thing, right? A lot of startups have shown very much, I mean, their algorithms, they developed so many algorithms. There's a lot of scope. Everybody wants people who knows quantum algorithms in quantum finance startups. And people are behind those people because a lot of money is there, right? And you can develop optimization solutions, take a portfolio. Portfolio optimization is the problem. They develop using this. Yes, sir.
When we are talking about the optimization problem,
Yeah.
so can we take any of the problems like we are just telling about the solution as the using of the enabling algorithm?
Yeah.
And if we just look into the optimization, we have got n number of the meta-heuristic algorithms.
Yes. Yes. PSO and all that.
PSO is
Genetic algorithm.
optimization is
Yeah.
there,
Yeah.
and column optimization.
Yes.
Can we use all those algorithms
Yes.
here
Yes.
for getting the
You can definitely try, sir. So these are some of the papers, obvious papers, right? Whether you get optimum result or not, because you don't know yet. So you need to determine whether your particular PSO problem. So for PSO, for example, particle swarm optimization, you picked some function, right? Some function you'll pick, right? That function, is it NP hard or not? First point you have to find out is that.
No, because when we are going with the PSO example, most of the functions what we have gone through, it has got NP-hard equations only.
Yes, if it is NP hard,
NP-hard.
then you can try on quantum, because otherwise it doesn't make sense. That's why I said you have to first know whether it is NP hard. If it is NP hard, please try on this. You get outcome. Try in classical, you will get an outcome. Compare the time. If this is more efficient, that is a paper. If it is not efficient, also that is a paper. If people would have not tried, I don't know.
And can we take some of the optimization, like we're just going for the electronic domain, we have got so many problems are also available in the electronic domain, we're just looking into it.
Okay.
Like, for optimization of the number of gates, for optimization of the power capacity being
Okay.
for that. Can we utilize into the quantum and go for into that direction?
We can go, sir, but like I said, you have to determine the problem is NP hard or not. That's the first step for any of this next steps. If it is NP hard, then you can definitely go and try, because we can't upfront tell that this will work or not. This is a trial and error only, because some algorithms work better. Like I said, the interference that we talked about in the morning, if the interference is helping you, the entanglement state is really helping you, it will work wonders, and it is a replacement. It's a replacement, quantum replacement of classical. If it is not, then it is not. So there is a segment of areas called BQP. I will show in the later slide. That they fall into that category. Instead of NP hard, BQP are the problems which are solved by quantum computers. They are best worked in using quantum computers. The reason quantum finance, quantum chemistry are shown are because they are proven that these are solvable by quantum computers and are much more efficient than classical. So if PSO, if you try here, and if it turned out to be efficient, because there may be somebody who might have tried, I don't know really. If it is efficient, then that is quantum suitable than classical suitable. So that
You need to say that whatever the existing algorithms are there.
every algorithm. So for learning purposes, you can try small algorithms, and every small algorithm will be best suited for classical computer only, not quantum. Though it fails with quantum, you will get an understanding on how to apply gates to begin with. So like morning I was telling about k-means and q-means, right? So k-means works wonders with classical computing. Why do we have to go with q-means at all? But the reason we went with q-means is to find out how can we transition from classical to quantum by putting various different. So we wrote code, tried it on IBM, and got the outcome, and then we have put that in the paper. That's how it is. So you can try to experiment and see if it works. Generally, it is like all the obvious classical solvable applications are not, are can't beat. I mean, quantum can't beat those. So quantum is not a replacement for classical computations. It is just that there are certain narrow set of applications which can only be solved by quantum and not classical. Those are the applications we need to find. That space is very narrow, NP. So we take NP hard by default, try with this. And if it works, it works. If it doesn't work, it doesn't work. But there is another category of complexity, which is exponential algorithms, which will not work with quantum also. You don't have to try at all. So we need to categorize the problem statement, whether it is NP or not. If it is NP, then try. That's how it is. Yeah. So machine learning, I think most of you know, one of the important applications that some of the companies are using is to train the large language models. Large language models require a lot of training. They need a lot of data sets, and not all data sets are suitable for using quantum computation. There are certain data sets which are suitable to be trained using quantum computer, just to make it faster in training, not to get any other thing, right? So you need an LLM which is trained. Let's say Meta has Llama 3. They want to kind of create Llama 4 or Llama 5, for example. I think they have Llama 4. Llama 5, if they want, they have to train with a lot of data. Now that data, they can train using the traditional GPUs over and over again. But if you want more efficiency, not for all, it doesn't work for all the data sets. Certain data sets, quantum computer is best solution. So for such machine learning, quantum machine learning can be used. So for training GPT kind of models, because some of the matrix multiplications are faster in quantum than in GPU. Not all, some. That is again this, say, it's always like constraint for everything. The last but important, which Manish also discussed in the morning, is that this application keeps governments awake at night, cryptography, because your RSA algorithm can be broken anytime, they say, but of course we don't have hardware. But once we have hardware, it will be definitely be broken. So the Shor's algorithm is a threat for us, because the algorithm is giving us a solution to give factors. But we don't want that to happen. So people are trying out with quantum key distribution, which is the solution to this. Four of them which are popular. The popular one is Qiskit, Cirq, Penny-Lane, and Q-Sharp. Starting with Q-Sharp, right? Q-Sharp is a full-fledged programming language developed by Microsoft, which is coming along with .NET, and it is analogous. Whoever has .NET or C# experience can easily understand. In fact, Microsoft is betting high on distributed quantum computing, and Q-Sharp has features which will help in distributed quantum computing kind of areas. Penny-Lane is also, it's very good for quantum machine learning, because somebody who is want to implement quantum computing in deep learning, Penny-Lane is the obvious choice, because it has a lot of add-ons and modules that can help building math and math kind of functionality. So it is obvious choice for quantum machine learning. Cirq is from Google. Google has put a lot of investment on this, but then there's a caveat on Cirq, is that it is hardware specific. So today you develop programs on Cirq, and tomorrow you decide that I want to use it on IBM or some other hardware, it doesn't work. So it is hardware. So they have made it like you work on Cirq, you have to use our hardware. So that's Cirq. Qiskit is hardware agnostic. Penny-Lane and Qiskit are hardware agnostic. So Penny-Lane works on any hardware. It works on quantum simulators also. That is the beauty of Penny-Lane. Why quantum simulators? Because quantum simulators, like morning sir has brought up a question. IBM is charging me for using qubits. So you tomorrow prepared an algorithm, or you created an application you want to test. So you don't have a quantum computer. So you have to log into IBM and create an account. They give 10 days free or 7 days free. And within 10 days you have to do it, otherwise you have to pay, unless somebody is sponsoring you. But if you have a simulator, you can install it on your laptop and you can try it out. It doesn't show any much difference. There is some latency, but it's okay for initial level of learning purposes. So if you are using Qiskit, Penny-Lane is your nice. Even Qiskit will work, but Penny-Lane is much suitable for hardware agnostic. So Qiskit is also hardware agnostic. So it is very Pythonic in nature, and it works with all the different hardware. But obviously, whoever is using Qiskit will work on IBM hardware. Yeah. So that's the last slide, but I will quickly go to the next slide. I do have 4 more slides. The reason I want to go is just cover a little bit of complexity theory, because this is this connects why, where, and how we use quantum computing. So complexity theory is not asking, can this problem be solved? It's not asking, can we solve this problem? It is only asking how hard the problem is. When it grows, that is important problem. That is important statement. For small dimensions, problems can be solved. The same problem that is solved with lower dimensions need not necessarily be solved using higher dimension because of the hardware problem. So we kind of tend to give relativity by introducing whether hardness means time, steps, how much time it will take to solve a problem, how many steps, resources, or how much effort we require, right? So it's not, so this is about scaling, not difficulty. Can we scale? When the problem statement or dimensions grow, can the problem be solved? That is what complexity tells us. So these are the different classes of complexity. P is polynomial time, which is generally called as easy segment, easily solvable. I'm sure most of the computer science staff here would know this, but I don't know the mix of the diversity of people over here, so that's why. So NP is a non-deterministically polynomial. NP complete is another set, the hardest of the hard. Exponentially is where everything fails. So no matter what you apply. So here quantum impact I have written. As you can see, for polynomial, quantum computers can solve it. NP, it is variable, means for some it can solve, for some it cannot. NP complete also it's limited. For exponential, so far it has not solved anything. That means it probably won't solve even for quantum computer. So having quantum computer doesn't mean that it will solve everything. It really depends on the problem statement and more dependent on whether that interference works or not. So that's what we are going to summarize. It is quantum computation will give us new physical capability, right? Capability we are getting. But quantum computer does not mean parallel computer. It is not doing parallel. It is in fact going to give us, somebody in the morning said, constructively, destructively. So basically it is interference, right? Wave nature, the quantum state vector will act like a wave. So if the computation adds the paths to be constructive in nature, is when it will allow the efficiency. So that is what I want to give as a notion to take away, that how well paths can be aligned. That's important. And how do we know that upfront? We don't know. We have to do trial and error. We have to keep, like sir asked whether I can apply PSO. Yes, please apply and try. If it does, it does. If it's not, it does not. So that's important. So we should not think that we have quantum computer, we can solve everything. It doesn't solve. Exponential cannot be solved. So far not proved. Yeah. Okay, that's all I have. Actually. Yeah. Any questions, anybody? Yeah, thank you. Mail ID. Yeah, I can. Yeah, I have. Yes.
If I ask the writer today to complete in single line, what is the moral of the story and how much it is?
Moral of the story. Moral of the story is that, like I said, so I just want to cover the basics of. I just want to cover the basics of quantum mechanics and how that quantum. Oh, is it okay? I just finished. Okay. So it is like how the quantum mechanics has been, why quantum is required from classical. We saw the three experiments in the beginning. We transitioned to quantum mechanics, and from quantum mechanics, how are we relating to quantum computation? Between that, we have some math. Why we need that phase, right, in complex numbers, because that is continuing the time and oscillation, and those things carry forward. And in the end, the quantum computation, we are mapping the operators, Schrodinger equation. The wave function is nothing but a state vector here. So operation. So basically, in quantum mechanics also, they are doing the same thing, right? They're solving the quantum systems using Schrodinger equations and applying operators. In quantum computation also, we are doing the same thing, but in matrix and linear algebraic way. Both are domains which are trying to solve problems for different purposes. Right? In quantum computation, we are more focused on our application. It's an application relying on quantum mechanics, some of the principles for solving these algorithms, right? We need, so that's why we have defined the continuous time evolving space to definite 0 and 1s and cut short into Dirac notation. So took the same things, but we formed a matrix gates instead of operators and trying to manipulate bits here. There we are manipulating the continuous equation by applying complex numbers and integration over there. Here we are doing linear algebra and slowly transitioning into gates, manipulation of bits, then formulating quantum circuits using the gates. And the circuits, how will you formulate the circuit? Based on your algorithm. So you take an algorithm, formulate what is the manipulation required for a given input. So for every algorithm, there is a function that you are trying to solve. That function you have to translate into this circuit. The circuit input and output is nothing but a mathematical function, right? And that you have to translate back again to your measurement. I didn't talk very deep into measurement, but then I told that the measurement in quantum mechanics is collapsing of wave function. Here you measure it and you get a real number, not a complex number. So that's a transition. And then I switched the gears to hardware to tell you different. So this is just a overall foundation that I think the next sessions would probably add on and give, I think. Yeah. Yeah, they're available. You can use. You can download in your own laptop. You can download and do a pip install. Yeah. Yes. You can try. I'm sure there are some labs in the next FDP sessions. They might tell you to install, probably give you a procedure to install and use. I didn't cover all that because it will be overlap. I am trying to minimize the overlap as much as possible. Yeah. Yeah. Okay.
Great session.
Because it doesn't make sense last time.
ये हमारा है, ये तुम्हारा है,
अच्छा ये भी हमारा
ये भी तुम्हारा है, लाओ उसमें रखता हूँ।
हाँ इसका ये निकालना है
तो ये हमारा ये
This penny layer and these softwares will not be.
I kindly request the participants to stay back for a while. Thank you, sir, for the detailed session on quantum computing and making us understand about the differences of classical computing and quantum computing. I kindly request Dr. Tabasumara to hand over the token of gratitude to Rajasekhar, sir.
One more minute, sorry. There? They will never create file. They open it once. They will.
Hello.
Your signature is required. Later through UPI non-negotiable. Sir, this PPT will share with us.
Yes, ma'am. I'll send you in WhatsApp.
I'll share. Sign.
Okay, ma'am. Nice meeting you.
Right, nice meeting.
Thanks for the opportunity.
Yes, sir. I'll connect you for some other.
Sure, ma'am.
Plant.
Close to me.